Welcome to Unit 4, the first section of which is on a topic called antiderivatives, which can also be called indefinite integrals. Really, this whole unit is on reversing the process of differentiating that we've been working on really for the first, 3 units of the year. In math, of course, we like to be able to reverse things, so here we are talking about antiderivatives. More commonly, the process is called integration. I'll probably go back and forth between the two. Let's start out with a question. If g prime is 6x squared, so they're giving us a derivative and asking us to find what the original function was before it was differentiated. A couple things to take note of here. First of all, g is a polynomial function. We like differentiating polynomial functions because they're usually pretty simple. You can use power rule on it, and quite frankly, anti-differentiating polynomial functions is not too difficult to do either. You just have to reverse the power rule. The power rule would also tell us that to have gotten from g to g prime, the power had to have dropped by 1. Well, that means since we're sitting at a power of 2 right now, the old power on g, the original power, must have been a 3. So we already know that the power in our answer, the power to our antiderivative, is going to be 3. Now let's focus on the coefficient. To go from g to g prime, applying power rule means you bring down that original power and make it a coefficient. You are essentially multiplying the function by whatever the original power was. Multiplying by the original power. To undo that process, instead of multiplying by the original power, we are going to divide by the new power. This is how you undo the product rule. So specifically with 6x squared, we already said the solution, we have an arrow here, not an equal sign, because a function's not going to equal its derivative usually. But we already said our solution is going to be something x cubed because the power must have, the former power must have been 1 higher than what we see in front of us in the problem. So to take care of the power, you kick it up a notch. To take care of the coefficient, you divide by that power. So I'm going to take the old 6, divide it by the new power of 3, and of course as a result I'd get 2x cubed as my antiderivative of 6x squared. We can check that pretty easily. Let's take 2x cubed and differentiate it using power rule, and lo and behold, you get 6x squared. Wouldn't 2x cubed plus 1 also have been an appropriate solution? Because if g of x is 2x cubed plus 1, g prime of x would be, let's see, bring this down, you get a 6x squared, and then, oh my goodness, that constant at the end drops off. Well, that is quite a conundrum. Here's how we take care of that. We aren't going to have one specific solution that is the solution. We are going to have what is known as a general solution in this case. We would say that the general solution to g prime of x being 6x squared is g of x is going to be 2x cubed plus whatever constant you want it to be at the end. And that takes care of every single possibility with that plus c. So it's understood here that that plus c is a constant. Specifically, they call it a constant of integration. Notationally, here's what we see. The integral sign, if you want to keep from having to say, what is the antiderivative? What is the antiderivative? In math, of course, we like symbols instead of really long polysyllabic words. So we use symbols. This elongated s, oops, This elongated s that you see here is an integral sign. The fact that there are no numbers here or here, which we will see later, makes this what is known as an indefinite integral. That's all we're going to be dealing with in this section. Don't worry about definite integrals quite yet. This dx is also going to be more relevant down the road, but it is nonetheless important and is a necessary part of every integral. You need that differential in there. You can think of it for now maybe as your in terms of x. So we're integrating or anti-differentiating with respect to x. For now, that's going to suffice, I think, for why it's there. It's more important when we talk about definite integrals. And then the plus c at the end of the solution is what makes this antiderivative a general solution. Every single one of your answers today should have a plus c in it. Let's talk about some basic rules for anti-differentiating, and they're pretty quick. The first one is really just undoing the power rule. So if you are integrating x to the n power with respect to x, by the way, n has to be part of the real numbers in order for this to work. It doesn't work when there is an imaginary number or a variable in the exponent. Furthermore, n can't be -1. But if this is just asking you to undo the power rule, just like in the example we just did, what you want to do is bump that n up to an n+1 and also divide by n+1. And don't forget your constant of integration at the end. I like to think of this as up a power and then over that power. Because that's really what you're doing. You're going from n to n+1, that's your up a power, and then by also putting the coefficient over that number, n+1, you're writing your answer over that power as well. Up a power over that power. A really basic version of this that sometimes trips people up till they get used to it is just integrating dx. You can think of that as like 1 dx, I guess. Or like x to the 0, because that's 1, x to the 0 dx. And if you apply power rule toward x to the 0, it would become x to the 1 over 1 plus a c. Well, x to the first over 1 is just x. Oh, by the way, do we see why n can't be -1 in this problem? Might have something to do with the fact that if n were -1, your denominator would be 0, and that's, of course, a no-no. There is a way to integrate x to the negative first that we will, again, talk about down the road. We'll kick the can in this down the road a little bit. But I guess that's that much less you have to worry about right now. If you were to have to anti-differentiate a constant, you could certainly take that constant out front, just like you could with limits and just like you could with derivatives, and simply integrate the remaining functions. Then your answer would be k. That would be part of the answer. Then again, integrating dx just gives you x plus c. I guess maybe I should mention one other here. Again, just like with limits and just like with derivatives, if you have to integrate a polynomial, you can certainly integrate that term by term. You can rip apart the terms. So the old pull the constant, rip apart the terms properties that applied in limits and with derivatives is back again in antiderivatives. And so then a couple quick trig ones. We all know that the sine and cosine, they are just the opposites of what they were when we were differentiating them. So differentiating sine gave us positive cosine. Anti-differentiating sine will give you negative cosine with a c. If you don't believe me, just take negative cosine and differentiate it. You'd get negative sine, which is positive sine. Vice versa, the integral of cosine will be positive sine. Because if you reverse the process differentiating the result, differentiating sine would indeed give you the original cosine. Some examples. Let's just integrate 5x dx. Well, you can take that 5 out, it's a constant, and then you're just integrating x dx. So you know there's going to be 5 as part of your answer. Integrating x, you can just apply power rule. X to the first, when you integrate it, becomes x squared. So that's up a power, and then also over that power. I guess to kind of clean it up, you could call that 5/2 x squared plus c. If you wanted to call it 5x squared over 2 plus c, if you wanted to put the x squared up with the 5, that is, of course, acceptable. If you're integrating 7x plus 3 dx, I'm going to need parentheses on this because there are more than one term in the integral. So what I'm going to do, just showing some properties here, I'm going to have an integral of just 7x, and that 7 is a constant, so I can take it out front. I'm going to give each integral its own dx, its own differential. This term gets its own integral. I'm going to take the 3 out front as a constant and just integrate dx. So we end up with 7, and then this x integrates up to x squared over 2. I could certainly put a plus c at this point. However, I'm also going to have a plus c after this, and since it's a constant plus some other constant, the result would just be a constant anyway. So I'm just going to save the energy and write 1 plus c at the very end. That will be a combination of both of the integrals constants of integration. Anyway, so this will be a 3. Integrating dx is just x. I would put a plus c at the end. I guess to clean it up a little, I'd get 7/2 x squared plus 3x plus c. There. Let's integrate 3 sine x dx. Again, that 3 is a constant. It can come out, and so then we're just really integrating sine x dx. We have a rule for that. Integral of sine is negative cosine. If you don't put parentheses on this step, if you just put 3 and then negative cosine x, it looks to every single person who knows anything about math like you intend to say 3 minus cosine x. In fact, that is literally what you would have written. Even though you aren't thinking that at the time, it doesn't matter. So just, if you're going to write it this way, be sure you have the parentheses. An even better way to do this really would just be to take the negative 1, write it out front, and call it negative 3 cosine x plus c. But no matter how you slice it, don't call it 3 minus cosine x, because that's just dead wrong. And very commonly done. All right, a couple more here. Let's do 5 over x squared dx. Just like with power rule, if you were going to differentiate this thing, it would behoove you to write it as maybe x to the negative second. And it's really the same idea with anti-differentiation. That 5 is still a constant. I can still have that out front. But I'm going to call this x to the negative second as my integral instead of 1 over x squared. Because now I can just undo the power rule with it. X to the negative second, when you go up a power from negative 2, you're at negative 1. And then you also put that over that negative 1 with your constant of integration at the end. And this cleans up to simply negative 5. That's what the 5 over the negative 1 is. That's where the negative 5 comes from. And then x to the negative first power is just like x to the first power written in the denominator. So we really just have negative 5 over x plus c. All right, one more here. This one will be a good one. Let's integrate. Yeah, we don't have to use x all the time. Let's do t. 3t squared minus 2t plus 1 all over square root t with respect to t. And oh my goodness, this looks scary. And in a way it kind of is. But again, it's just a long problem. It's not a tough problem. We're just going to basically do 3 little problems in one. We're going to have to blast this numerator into 3 different fractions. Since there is a common denominator here called square root t, I can write this as this integral minus this integral plus this integral. So I've really got integral with a 3 out front, t squared over t to the half. I'm going to call this square root t, t to the half. That's our first integral. Then I got a minus 2. I'm going to take that minus 2 constant. My integral then becomes t over t to the half, dt. And then I've got a plus, the 1 doesn't really do much for me here. I've just simply got 1 over t to the half. I could call that t to the negative half. I'm going to start a new page here. When you're dividing powers that have the same base, you can subtract the exponents. So this is really t to the, if you got 2 and you lose a half, you've still got 1 1/2. So that's 3 halves. Here if you've got 1 and you take a half away, you still got a half. And now it's just going to be up a power over the power, up a power over the power. Up a power takes you from 3 halves to 5 halves. Up a power from 1 half takes you to 3 halves. Up a power from negative half takes you to positive half. And then, you know, you're dividing by fractions. My goodness. Dividing by 5 halves is just like multiplying by 2/5. Dividing by a fraction is just multiplying by its reciprocal. Don't be alarmed. So really we've got 3 times 2/5, which is 6/5. Here we've got 2 times 2/3, which is 4/3. Here we've got something divided by a half. That's like something times 2. And frankly, that's fine. You don't have to factor stuff out. You know, your book probably will. Do it, don't do it. This is fine. You can write things as radicals. If you have the correct simplified power, I'm fine with that. So these are kind of introductory problems. It's just really getting practice with undoing the power rule. We will obviously go and do other things with it down the road, but for now, please just enjoy the simple, albeit maybe a little tedious nature of some of these introductory problems.